Okay, great. All right. Welcome here today. Okay, so in the last meeting, what we did was we discussed the Vesper model and the relation of Vesper to molecular polarity, right? We determined that some molecules are polar based on their shapes, but the shapes are determined by the Vesper model. And the Vesper model is predicated, it's based on the idea of Lewis structures. So we spent, much of chapter 8 dealing with Lewis structures, how to draw Lewis structures. And then even into chapter 9, we're doing Lewis structures. What we're going to talk about now is a modified theory, or a different theory, actually, about chemical bonding. And so I want to point out that there are multiple theories that chemists use to describe chemical bonding based on the situation. So for example, if we want to figure out the shape of a molecule, we might use Vesper theory. If we want to look at, some of the optical properties of materials, like how they transmit light or how they reflect light or how they absorb light, we might use a different theory. So there are multiple theories out there. The two primary theories, one is called valence bond theory, as in the valence shell. And the other one is called molecular orbital theory. And the molecular orbital theory is what we'll talk about in the next lecture. But today I want to talk about valence bond theory. And for the most part, practical chemists, meaning people that are working, trying to figure out how to make molecules and things like that, they will use primarily valence bond theory. But people who are chemists or physicists or engineers that are really trying to figure out like the structures of molecules and explaining their optical properties, they will often use molecular orbital theory. Both of these theories are just they're theories. They are able to describe many phenomena that we observe in nature, but not all of them, which means that neither theory is complete and neither theory is completely correct. Just like Newton's theory of gravitation is a great theory and it works for sending rockets to the moon or spaceships out to Pluto. It works very well for that stuff. It works for artillery shells, airplanes. It does not have the ability to accurately describe the properties of galaxies, right? So if we want to describe the properties of galaxies, we need Einstein's theory of relativity. So the same is true with chemical bonding. None of these theories that we describe here are complete and perfect. Quantum mechanics is a very complex phenomenon. And there are even more advanced theories that we could use, but they're just beyond the scope of this course. It would just be too much for us to be able to deal with that in a course like this. So that's left to researchers. So we're going to talk today about valence bond theory. And I guess just to make it simple, we'll call it VB, valence bond theory. Okay. Valence bond theory, in a sense, we've been kind of doing it a little bit with our Lewis structures. Lewis structures lead directly into valence bond theory. Valence bond theory is based on the following idea, that we're talking about covalent bonds. Covalent bonds are a result of the overlap of atomic orbitals from different atoms. Okay, so that's essentially what it is it's claiming that a covalent bond is what happens when atomic orbitals overlap with each other. And we can take that a little bit further and claim that the greater the amount of overlap between these orbitals, the stronger and shorter the bonds are. Okay, so the idea is that the greater the overlap of these atomic orbitals, if there's more overlap, the bond will be stronger. If there's only a little bit of overlap, the bond will be weaker. The stronger a bond is, in general, the shorter it is, which is interesting, meaning that if you have a large amount of overlap, the atoms tend to be close to each other. The further apart they are, the weaker the bond is. So bond length is actually can be used to kind of figure out how strong the bond is. If it's a short bond, it's probably a stronger bond. If it's a longer bond, it's probably a weaker bond. Okay. Now, how do you measure the length of a bond? We've never really talked about that. We can actually look up numbers. We have lengths of bonds out there you can look up. It's pretty simple, actually. At least for solids, it's pretty simple. What you do is you make a crystal. So you crystallize something, like you make table salt as a crystal, right? And then you shoot X-rays at it. And the X-rays will diffract off at specific angles. And the angles are dependent on how far apart the nuclei of the atoms are from each other. So the closer the atoms are to each other, you'll have a particular angle. If they're further apart from each other, it'll be a different angle. And you can essentially use that angle to figure out how big how far apart the nuclei are. So essentially what you do is you say, hey, here's the nucleus for one atom. Here's the nucleus for the atom that's right next to it, right? There's going to be some distance between them. And we'll just call that the bond length. So you're not really concerned about the structure of the atom or anything. You're just saying, look, there's a distance between these 2 points. Remember, a nucleus is really tiny. It's a point. X-rays can measure that distance, and we'll just call that the bond length. That's how far apart the 2 nuclei from each other. Okay. So here, let's get to this issue. It's very interesting, right? So if you take this, let's take the simplest molecule we can imagine, which is H2, dihydrogen, right? Here's our Lewis structure for it. There's H2, right? Single bond, right? 2 electrons holding the atoms together. In fact, we could even draw it like this, right? There's a molecule, covalent bond. If you consider the orbitals of the hydrogen atom, you have the 1s, right? So the hydrogen has 1 electron in the 1s orbital. There's also other orbitals, right? The hydrogen also has a 2s, right? But actually, let me draw it down over here. Remember, we have the 1s here. And then the 2s is higher in energy, right? And it's empty. There's nothing in the 2s orbital. Hydrogen only has 1 electron. In fact, it doesn't even have enough electrons to fill up the 1s orbital, right? And then you got your 2p's, right? The 2p's are up here. So those are all orbitals, but they're all empty. And in fact, in terms of chemical bonding, we can ignore them because there's no need to use them for chemical bonding. But this orbital right here, that one's useful, right? So here's essentially what we're going to claim. We're going to claim that when you have a hydrogen atom, the only orbital that's important, really, is the 1s orbital. And what does a 1s orbital look like? It looks like this, right? That, of course, is a gross simplification of what it looks like. It's actually a probability distribution, high probability near the nucleus, falls off exponentially as you get further away, but it looks something like that. We can represent it that way. What we'll claim is that the bond between 2 hydrogen atoms is what happens when these 2 1s orbitals overlap with each other. Okay, so here's the 1s. Let me move that H over a little bit. Here's the other hydrogen. And there's overlap between those 2 orbitals. This is called the region of overlap. Mathematically, actually, if you go on to take more advanced chemistry courses, not organic chemistry, wouldn't do it in there, But if you took physical chemistry, they would actually have you do something called an overlap integral, which is a mathematical process where you essentially do something called integration and figure out the region of overlap there. An overlap integral, it's called. Okay, so there's your H2 molecule, and we're going to claim that that's what the chemical bond is. The chemical bond is that space where the orbitals overlap with each other. The greater the overlap, the stronger the bond is. The greater the overlap, the shorter the bond is. And what we know is that the distance between the nuclei, right? I called that the bond length. The bond length is about 0.529 angstroms. Remember the angstrom? I mentioned that a few weeks ago, or a couple weeks ago. An angstrom is 10 to the minus 10 meters. So this would be 0.529 times 10 to the minus 10 meters. That's an angstrom, is 10 to the minus 10. It's a convenient unit. So the bond length between two hydrogen atoms is about a half, right? 0.5 is about a half of an angstrom. So it's approximately a half of an angstrom. Okay, so that's it. That's essentially the idea of valence bond theory, is that all we have to do to figure out how strong a bond is, all we have to do to figure out how short a bond is, or how long it is, really, is to figure out how much overlap there is between the orbitals. And the idea is that essentially atoms will use their orbitals to overlap with each other to form chemical bonds. And that's essentially the idea. So let me show you an example. Let's take the H2S molecule. Okay, I'm going to begin by drawing the Lewis structure for it. Sulfur is in group 6A. Hydrogen is in group 1A. So you've got 2 hydrogens, so 2 valence electrons. And then there's only 1 sulfur, so 6 valence electrons. So you got 8 valence electrons. And then we'll draw it like this. Remember, there's only 1 sulfur, so sulfur goes at the center. We've already used 4 electrons, so that gives us 4 left. So let's put them on the central atom. Remember, hydrogen only needs 2, duet rules, so we'll put them on the sulfur. And now we're done. So there's our Lewis structure. So when you start thinking about sulfur, sulfur is the central atom. And sulfur is, its valence shell is 3s2, 3p4. Okay, that's the valence shell. I've ignored the core electrons, right? It's element number 16, so it's 1s2, 2s2, 2p6, 3s2, 3p4. So there's your valence shell. The valence shell, remember this is called valence bond theory, right? So the valence shell is what we're concerned with. We're going to ignore the core electrons just like we did with Lewis structures. So notice you've got these p orbitals, right? And there's 4 electrons in them. And then you've got the s electrons and there's 2 electrons. This one's full, right? That's a full orbital, right? It's 3s2. So there's nothing going on there. That's not going to form any chemical bonds with anything. But here we have our 3p. Remember the 3p, there's 3 orbitals and there's 4 electrons. So 1, 2, 3, 4. Okay. Now look at here. Here's an orbital that only has 1 electron. Here's an orbital that only has 1 electron. Okay. So maybe these are the orbitals that are going to be used for bonding. And that's an important idea, right? It's the orbitals that are not filled that are going to be used for bonding, because if the orbital's filled, there's no room for any electrons. So you can't have any additional electrons coming in from another atom. So it's really just these ones that are half filled, the ones that only have 1 electron. Those are the ones that we're going to be concerned with. So here's essentially what happens with H2S. The sulfur has p orbitals. Now remember what a p orbital looks like, right? It looks something like this. Again, it's a gross simplification. Remember, there's a 3p orbital right there. So you got the p orbital here. And then remember, p orbitals are at 90 degrees to each other, right? They're 90 degrees. They're perpendicular to each other. So another p orbital is going to be like this. Okay, so this is a 3p orbital. Remember, the p orbitals have two lobes. They don't just have one lobe, they have two, right? So the whole thing, both top and bottom, that vibration is a 3p orbital. So here's the second one, right? This is also a 3p. I'm not going to shade that one in just to show you that it's a different one. Okay, so here's what we'll claim happens. We're going to claim that one of these orbitals is going to overlap with the 1s orbital from a hydrogen atom. So remember, hydrogen, it only has one orbital, 1s, and one electron. So essentially, this orbital here overlaps with this orbital here. They overlap. They form a bond. So I'm going to show that down here. I'm going to take my 1s orbital from my hydrogen. I'm making that way too big. Let's make it smaller. Here we go. So here's your hydrogen. There's your 1s orbital. There's your overlap. There's a bond. So now let me line this up. I'm going to line this up over here. Let me erase this up here and line it so you can kind of see it a little bit better. Okay. So sulfur, again, we're just concerned with the 3p because the 3p orbitals, so I'll write 3p under all of them, because those are the ones that only have one electron right here. So this one and this one. Then we're going to claim that one of the hydrogens is going to use its 1s orbital, right? So now these two orbitals are going to overlap with each other. So it's the orbitals that only have one electron. That's what a covalent bond is, right? Each atom donates an electron. But then you have another hydrogen, right? There's two hydrogens. It's H2s. So here's our other hydrogen right here, 1s. And so then the overlap is going to be between these two. Okay, so I've shown one of them here. Let's show the other one here. So there's your 1s and there's your overlap. So there's your bond, which you might think it's that one over there maybe. And then here's your bond, which might be that one over there. Okay, so again, this one, not an issue because that one's already got two electrons. It's the ones that have one electron. Because then if you donate the other atom, if the other atom brings an electron, now they can pair up. Now you may have noticed something kind of interesting here, which is see how these are both spin up, and that's not possible, right? If they're in the same orbital, that one's got to be spin up and one spin down. So in fact, what happens is one of them will spontaneously go spin down and then they form the bond. So overall, we're not going to talk about that in this yet. We'll get to that in a little bit. But one of them is going to be spin up and one's going to be spin down. So there has to be what's called a flip. One of them has to spin down. Okay. All right. So now what's the evidence for this? Is there any evidence that supports this idea that it's the overlap and they're attaching at the orbitals, right? Think of the atoms as attaching. Essentially, there is evidence. It turns out if you measure the angle between the hydrogens, this angle, it's about 90 degrees. It's a little more than 90. It's like 91 or 92, but it's essentially 90 degrees. So you say, okay, 90 degrees, where does that come from? Oh, right, the p orbitals. The p orbitals are 90 degrees with respect to each other. So if those angles are 90, if the orbitals are 90, then that means that these bonds must be using those orbitals, right? So this orbital is 90 degrees to that one. So yeah, it matches up pretty nicely. So for some molecules, it appears as though what happens is, an atom has an orbital with one electron. Another atom has an orbital with an electron. those two orbitals overlap with each other. You get a region of overlap, you have a bond. One electron spin up, the other one spin down, you got a covalent bond. It's just as simple as that. They just attach to the orbitals like that, okay? So that's a good example of one, H2S, okay? Now, let me show you, I'm going to see if I can go through this here. Okay, so we're going to have to do this. Okay, so now something interesting can happen when atoms are forming bonds. Let me show you what I mean by this. What I'm going to do is I'm going to consider the boron atom. Let's consider boron. Boron is B, element number 5. Molar mass is 10.81. We don't need that, right? But let's do the electron configuration. Boron has 5 electrons, so it's 1s2, 2s2, 2p1. Okay, so here's your valence shell. Remember, the valence shell are the electrons with the highest value of n. So in those electrons, n is equal to 2. So these would be valence electrons. And this would be your core electrons. Okay, so for chemical bonding, we said this a few times, right? For chemical bonding, we only need to worry about the valence electrons. That's why we did Lewis structures the way we did. Okay, now here's what I'm going to do. I'm going to show you a molecule that has boron. Let's make it a simple molecule with boron. It's called borane. Boron's actually a very interesting element. It's in a sense a little bit like carbon. It's right next to carbon, right? It's boron, and then the next element is carbon. So actually, the two of them are very interesting chemicals. I mean, two very interesting elements chemically. Okay, so there's a molecule. So you've heard of methane. Methane is CH4. Borane is the same thing. Borane is BH3. And you ask, okay, well, why is borane BH3 and methane is CH4? Why does carbon have 4 hydrogens and boron only has 3? And there's a very simple answer for that. Okay. Essentially, what happens is boron has 3 valence electrons. Carbon, on the other hand, let me do carbon over here. This one has 4 valence electrons. Okay. So essentially what happens with borane is this. Let me show you. We're going to deal with borane and then we'll do methane. Okay. What we know about borane, I'm going to draw your Lewis structure for you. Okay, so there's the Lewis structure. Notice it's non-octet, right? Boron is an interesting element in that it very frequently only has 6 valence electrons. It is possible for it to have 8, but it typically only has 6. It's very common, okay? What we know, here's our evidence about borane. It has 3 identical bonds. When I say identical, what I mean is the same strength. And our way of measuring bond strength was called bond enthalpy. We talked about that in chapter 8. So they have the same bond enthalpy. They're all the same strength. And they have the same length. Okay? So what that means is whatever is this bond is like here, this one is exactly the same, and this one's exactly the same. They're the same type of bond. They're not different types of bonds. Okay? So how do we get 3 identical bonds? Valence bond theory is based on the idea that the strength of a bond and the bond length, the type of bond you have, is all about the overlap, right? The orbitals have to overlap. So if all three bonds are identical, that means that the boron has to be using three identical orbitals. Okay, that's an important point. If the bonds are the same strength and length, the orbitals at the central atom, here's your central atom, the orbitals that it's using to form bonds have to be the same. So that presents a problem. Let me show you what the problem is. Here's the problem for boron. The valence shell of boron is 2s2 2p1. So if it's going to use three identical orbitals, which orbitals is it going to use? You might suggest that it's these three here. Maybe those three orbitals they would be identical, right? Meaning they would have the same shape, they would have the same size, they would be identical orbitals. It turns out that doesn't give you the right answer, because it turns out in order for that to occur, we would have to have one of these electrons up to here. It would have to get up to a higher energy. Remember, 2p orbitals are higher in energy than 2s. So one of those electrons would have to go up there. And then a second electron would have to go up to there. And that takes too much energy. The atom would have to, it would have to be an endothermic process to do that. So that doesn't seem to explain what happens. So then you might say, well, maybe only one of them comes up here and not the other. That would be less energy. Only one electron going up is much less energy instead of two. But there's a problem with that. The problem is the 2s orbital looks a lot different than a 2p orbital, right? Remember, here's your 2p and here's your 2s. They are not at all the same type of orbital. So if these are identical bonds, they have to use identical orbitals. That doesn't work either, because these are different types of orbitals. So what we know then is that boron's got to be doing something. It's got to be doing something different. It's not using a 2s because these bonds are the same. It can't be using all three of these orbitals because that would take too much energy. Furthermore, here's one more piece of evidence. What we know about boron is that not only are the bonds identical, they are 120 degrees apart from each other. This is known. This can be measured. And if it was using all three of these orbitals, they would be 90 degrees apart, right? These are all 90 degrees. So there's no way that it's using just p orbitals. So what's happening then? If valence bond theory is going to be used, we have to be able to explain what's happening. How are we getting 120? Remember, that's trigonal planar. So it's a flat molecule. If we're getting a trigonal planar structure, we have to be using three identical orbitals based on the bond lengths and all of that, bond energies. How are we getting three identical orbitals that are not p orbitals? And here's our answer. It's something called hybridization. Okay? Hybridization is a common method that we use to describe valence bond theory. It's called hybridization. Hybridization is the idea that atomic orbitals, because they are waves, can mix. So think about it this way. If I take a wave that's coming from a musical instrument and the wave that's coming from a different musical instrument, those waves can now mix to each other to give you a new sound. And that's essentially what these electrons will do. The electrons will mix with each other to form new orbitals. And those new orbitals have different shapes and different energies and different spatial relations. And it's really cool. It's called hybridization, the mixing of atomic orbitals. So that's what we're going to spend the rest of this section talking about, is hybridization. And the homework of problems on Alex are all about hybridization. So this is the mixing of atomic orbitals for the central atom to give hybridized orbitals, or hybrid. You can either call them hybrid or hybridized. Okay, so let me show you the possibilities. I'm just going to make a list of all the possible hybrid orbitals that you want to be concerned with. And then I'm going to go back and help you figure out how can you figure out which hybridization is it. Okay, so here are the possibilities. The first one is that you mix an s orbital with a p orbital. And now it's going to give you two new orbitals that are called sp. Okay. The shape of an sp is interesting. It looks like this. Here's the nucleus. Notice how it's only pointing on one side of the nucleus. So imagine this is the nucleus of the central atom. This orbital, this new orbital called the sp orbital, is going to be pointing toward the surrounding atom. So that means it's going to do a good amount of overlap with the orbital for that other atom. And that's essentially what happens. This wave right here, remember it's a wave, this wave right here, which might look different, they are going to mix to form two new waves. Okay. Those two new waves are called sp. And so how do we get the name sp? If you're taking an s and you're taking a p, we just call it sp. Right? S and a p is sp. Why are there two? There's a conservation law at work. If you are mixing atomic orbitals, the number of orbitals you get at the end is equal to the number that you put in. So you can't put in 3 orbitals and get 2 out. You can't put in 4 orbitals and get 5 out. If you have 1 orbital plus 1 orbital, you're going to get 2 new orbitals. Notice also these two point in opposite directions. So one of them is pointing to the right. The other one is pointing to the left. So that gives them directionality. So these waves are mixing so that they can point toward the surrounding atoms. That way they can interact with the surrounding atoms. Now, why would they do that? They don't have intelligence. They're atoms. They don't know what they're doing. They do it because the nucleus for the other atoms are positively charged. So these electrons are essentially trying to bond to the nucleus of the other atom. In a sense, that's what a molecule is, right? You have these nuclei that are positively charged. They don't want to get anywhere near each other. Simple repulsion. But the electrons, they're attracted to the nucleus. So they want to form some sort of relationship with that other nucleus. But they've got this problem. They have this other electron on the other atom that's repelling them. So what happens? Quantum mechanics. And this is the magic of our universe. The fact that if one electron is spin up and the other one is spin down, even though they repel each other, that energy of repulsion is small enough that they can interact with both nuclei and hold the two nuclei together. It is not something that's constant. There's a force of repulsion between the nuclei. There's still a force of repulsion between the electrons, but quantum mechanically, that spin up, spin down, the Pauli exclusion principle lowers the energy enough that it can hold those two nuclei together. It's an unhappy romance. Their molecules are constantly trying to fall apart, but they're also constantly trying to hold each other together. Okay, so this is called sp hybridization, and those are called sp orbitals. So each of these new orbitals is called sp, and there are 2 of them. The next is what happens when you take the s orbital and you mix it with 2 of the p orbitals. 2 of them. So what are we going to call that? We call that sp2. So notice if we put in 3 orbitals, we got to get 3 out. So there are 3 of these orbitals that are called sp2. So why sp2? Well, if you're adding an s, that's s. If you're adding a p, that's sp. But now we have 2 of the p's, so it's sp2. Okay? What happens here? Here's the nucleus of the central atom. You get 3 identical orbitals. These ones look a little skinnier because there's more p. Now we have 2 of the p's, so they're averaging. Essentially, you're averaging these 3 orbitals, just like we averaged those 2. So now you get this. You get 3 orbitals that are 120 degrees apart. So in fact, when we get to the problems, we're going to use the shape of the molecule to figure out the hybridization. We'll work backwards, okay? If you know the angle's 120, that tells you it's sp2. If you know the angle is 180, you know it's sp. And that's what chemists will do. They'll say, oh yeah, I recognize the Lewis structure. I can tell you the hybridization. So now I know the shapes of the orbitals, and I know their energies and all of that. Okay, let's look at the third one. There's only 3 p orbitals, right? There's, 3 of them. So you can only add 3 of them. So now we're going to add them all. We're going to add all of the p's. And so how many orbitals went in? 4. So how many orbitals do we get out? We're going to get out 4. These are all sp, and just kind of, analogous. If this was sp2, we're going to call this sp3. And here we are, sp3. What happens here? You get 4 orbitals. They're more pointy, and they're tetrahedral. 109.5 degrees. Tetrahedral. So see how this hybridization is, not only is it telling us how many orbitals there are, it's giving us information about the shape of the molecule. So in a sense, hybridization, well, not in a sense, hybridization is directly connected to Vesper theory. Another reason we like hybridization, it fits in well with another theory that we've already talked about, Vesper theory. Okay, 4 orbitals. So remember, this is the central atom. This is the nucleus of the central atom. We're ignoring the core electrons. These are new orbitals that are made from adding these atomic orbitals. It's a mathematical average, right? So they often use this analogy that if you take a horse and a donkey and you breed them together, they're slightly different species. They're almost the same species, but not quite. And when you try to breed different species, they can't breed, right? So you can't take a chimpanzee and a gorilla and breed them. They're different species. But a horse and a donkey are so close. They've only split within the last 1,000,000 years. You can get an offspring, and it's called a mule. But that mule can't reproduce, right? So it's a different species itself, I guess. But it's sterile. So essentially what's happening here is, what is a mule? It's an average of a donkey and a horse. It's in between. That's what you're getting with these hybrid orbitals. These hybrid orbitals are mixtures of the s and the p orbitals. So an sp3 orbital is more like a p orbital than an sp orbital is, right? An sp orbital is more like an s orbital because it's 50% s and it's 50% p. But here, this is only 25% s and it's 75% p. So the shapes are starting to change a little bit. Okay, well, we've run out of p orbitals, so what do? It turns out we can expand this to elements that have more electrons, the third shell. Because remember, S is important for the first shell. P is important when you get to the second shell. D is important when you get to the third shell, 3D, right? We don't have a 2D, but we have a 3D and we have a 4D. So what happens is if you get into the third shell, so this is the third row of elements and beyond. So you can go to fourth and fifth. Then we can have even more. So we're going to do S plus P plus P plus P. And then one of the Ds, we're going to add a D orbital. So you wouldn't see this in carbon or nitrogen because they're in the second row. But when you get to the third row, like chlorine, sulfur, phosphorus, that's third row, you can have D. When you get to the, so what is this called? So we're going to add S, P, D. So I'll write them out here. How many are we going to have? 1, 2, 3, 4, 5. And these are all, I'm not going to write them for each one. They're all the same. These are called sp3d. Okay. sp3d. Why? You have an S, you have 3 Ps, and you have a D. Okay. And again, this is only good for third and fourth and fifth row. You can't use it for the second row. Second row, there are no D orbitals. So what happens here? You get 5. There's 5 of them. Why 5? 5 orbitals in, 5 orbitals out. They're all equal to 8. Now they have some D in them. So, oh man, what are their shapes? So now you got S orbital, you got P orbital, you got D. What's the shapes? I don't even know what the shapes are, to be honest with you. They get more complicated. But I'm just going to kind of draw them generically like this. Okay, so there's 5 of them. And what you end up with is you get that shape that we talked about before, where you have the 90 degrees here and you have the 120 here. That was our trigonal bipyramid. So again, it connects very well in with Vesper theory. You get the same angles. In fact, it's like you measure and that's what you get. You actually see those angles. So that tells us there's something, there's something probably pretty valid in this theory. Again, chemists use hybridization as a very mainstream theory. The last one that we would concern ourselves with is what happens when you mix the S with all the P's and 2 of the D's. Okay, so you got 6 of them now. So remember linear, trigonal planar, tetrahedral, trigonal bipyramid? The last one is octahedral, if you remember from Vesper theory. So now you get 6 orbitals. 1, 2, 3, 4, 5, 6. sp3d2. Why d2? Because there's 2 orbitals, 2d orbitals. This one's your octahedral. Right, 90 degrees octahedral. Okay, so those are the only hybridization ones you need to know. That will get you through all of the homework. There is no test. You don't have to take a test on chapter 9. But for the homework, this is it. Those are the ones. SP, SP2, SP3, SP3D, and then SP3D2. So now I've shown you what they are. I've shown you the kind of the shapes of the orbitals. Obviously, you can look online and find beautiful pictures of these things. How do you do the problems? How do we use all of this background theory or background information to figure out how to solve problems? Essentially, what we do in this course is we ask very simple questions. So the first question is, given the formula, so if I give you the formula, you want to find the hybridization of the central atom. That's what you want to be able to do. Okay? There's one other type of thing that we want to be able to do, and we'll get to that in a moment. But for right now, all we have to do is essentially say, oh, it's sp2. Or, oh, it's sp3d. You know, that's essentially what you want to do. But then in keeping with that, you should have some idea that, oh yeah, if it's sp3, there's 4 identical orbitals and they're tetrahedral, right? So I'm just going to make a quick little table here. sp, there's 2 orbitals, and it's 180 degrees, which is linear, right? sp2, there's 3 orbitals, 120 degrees, trigonal planar. sp3, 4 identical orbitals, 109.5 degrees, tetrahedral. sp3d, 5 identical orbitals. Remember, this one was 90 and 120, and this is your trigonal bipyramid. And then sp3d2, 6 identical, 90 degrees octahedral. Okay, here's how you do it. It's very simple. Do you remember when we talked in section 9.1 about molecular geometry where we counted up electron domains? Okay, same thing here. You count electron domains. Okay, and the electron domains match up perfectly with this table right here. So I'll make one more column. Here's electron domains. So here's your shape. Here's your angle. Number of orbitals. And then there's your name, right? That's your name of the hybridization. 2, 3, 4, 5, 6. All you got to do is count up electron domains on the central atom. Okay? And you've got your answer. Now remember, when we count electron domains, a single bond is 1. A double bond only counts as 1, right? And a triple bond counts as 1. And a lone pair counts as 1. That's what you got to keep in mind. When you're counting electron domains around the central atom, each of those counts as 1. And then you just use this table and you've got it. Boom. Okay? So let me show you an example from Alex. So they want you to find the hybridization of the central atom of borane. Well, that brings us back. I never even answered that question. We talked about borane at the beginning. How do we do this? You draw the Lewis structure. Okay, we did do that part. Count up the electron domains. Boron has 1 electron domain, 2 electron domains, 3 electron domains. So 3. 3 electron domains is sp2. And there you have your answer, sp2. Okay, very simple. Let's try another one. They want you to do the, I'm going to try to do this one down here. Let me erase this because I have that table there. So this one is chlorine pentafluoride. So they tell you it's ClF5. Now here's a little kind of a tip. Look at how many surrounding atoms are. There's 5, right? So that right there tells you it's got to be one of these ones down here. If you have 5 surrounding atoms, you got to have 5 domains at least. The only question is, do we have any lone pairs? If you have a lone pair, that'll give you 6 electron domains. If you have 2 lone pairs, now you have 7, and we've got a problem here because I didn't go up to 7. It turns out that's a problem. You can't have more than 6 usually. So anyways, let's do the Lewis structure. This one's a tricky Lewis structure, okay? So we know there's 5 surrounding atoms. So I'm going to draw them like a pentagon. Okay? 5 surrounding atoms. Okay, now we got to count up all the electrons. Chlorine is in group 7A, but so is fluorine. They're both in group 7A. So that's 7 electrons for the chlorine, but there's 5 fluorines, so 5 times 7. So you got 42 electrons. That's a lot. But we've already used 10. So we're down to 32. Now, remember this, the 6, put 6 around each fluorine, because that will get, remember, the surrounding atom never has more than 8. So you don't have to worry about expanded octet for the surrounding atoms. It's only the central atom that can be expanded octet. So I'm a little bit out of room here, but let me write them like that. So there's 30. 5 times 6 is 30. So then we said if you have any left over, oops, you put them on the central atom. So there, I'm going to put it on the central atom right there. Okay, now we're done. So now, again, come back to the table. How many electron domains? A single bond is a domain, a double bond is, a triple bond is. We've got 5 single bonds, so that's 5 domains on the central atom, but we also have a lone pair. So there's your 6th. So what do we get? We get sp3d. I'm sorry, sp3d2. So there are 6 electron domains, 6 orbitals, and the name of those orbitals is sp3d2. Okay? It's actually pretty simple once you've got that table. But notice, we also want you to know, like, look, what are these hybrid orbitals? They're the mixing of all these orbitals. And why do they do it? Because the central atom is trying to form a bond to all these other atoms. So how does it do that? It's got to hybridize these orbitals in order to make equal bonds that have the same strength and the same bond length and all of that. Okay, let's look at one more. Oh, man. Okay, here's, oh my goodness. Oh, let's do this one. This one looks like a challenge. I've never seen it before, to be honest with you. Br3 minus anion. Interesting, Br3. So what do you do when it's Br3? When there are, so sometimes people often wonder, like, can you have molecules that have like a ring? And the answer is, if there's only 3 atoms, you probably can't. It's very rare. So avoid that. There are, there is this really famous molecule in organic chemistry that's 3 carbon atoms in a ring, but it's very reactive. You could use it as an explosive. It's so reactive. Generally, what happens is the orbitals, the angles are not right, so the bonds break. So you can't form 3-membered rings. If you have 4, 5, 6, then the angles are not strained so much and you can have rings. So 6-membered rings are very common in nature. So are 5, but 3 very rare. So that means we're just going to draw the Lewis structure like this. Okay, that's more obvious. I mean, more common. Okay, so now once you've got these 3 atoms, we're going to do the Lewis structure, right? Remember, for the shape and for hybridization, it's only the central atom we're worried about. So we're just trying to figure out what the central atom is doing. Okay, so you've got how many electrons? Bromines in group 7A, so you got 3 times 7. And then it's negative, so you got to add 1 more, so that's 22. We've already used 4, so you got 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh my goodness, we've still got 6 left. We got to put 6 electrons around this central atom. That bromine actually has 3 lone pairs. That's a crazy structure. I have no idea how stable this tribromide anion is. I've never seen it before, so I assume it's pretty reactive. But in any case, very simple idea for hybridization. You count up the number of electron domains. So remember, here's our name, sp, sp2, sp3, sp3d1, sp3d2. The number of electron domains, 2, 3, 4, 5, 6. Okay, so we've got a single bond here, a single bond there, so that's 2, 3 lone pairs, so that's 5. There you go. So that means that bromine in the center is actually sp3d, which is 5, right? There's 5 orbitals. So essentially what happens is you get a bromine here, you get a bromine here. This is really Vesper theory that I'm doing right here. 3 lone pairs in the center. Isn't that cool? So 5 electron domains. Of course, the whole thing is negatively charged, so I'll put a bracket around it. 3 lone pairs on this one, 3 lone pairs on this one, and there you go. Okay, kind of cool. So sp3d. All right, and let's see. Okay, let me do one more. So this is very important. So the second type of problem is carbon. They're going to focus on carbon. And the reason they focus on carbon is that hybridization was invented to explain the chemistry of carbon. It works perfectly with carbon, absolutely perfectly. It does not work perfectly with other elements, but it works perfectly with carbon. So organic chemists, because they're interested in carbon, because biochemists and molecular biologists and cell biologists and geneticists, they're all working with carbon, right? Carbon is the important element for life. Hybridization is perfect for it. So here's what they're going to do. They're going to give you a larger molecule, but it's going to be a really simple molecule. It's just going to be like hydrocarbons, but they're going to give you more carbons, more than one. And all you have to do is figure out the hybridization of the atoms, of the carbon atoms, okay? So what they do in this one is they say, how many carbons are sp hybridized? Okay, so there's your question. And the answer could be, one of them, because there's 3 carbons, or none. So you got 4 possibilities, right? Either all of them are, or none of them are, or one of them are, or 2 of them are, right? So 1, 2, 3, or none. Very simple. You just go one by one. You look at this one here. Let's start with this one on the left. How many electron domains does it have? Remember, a single bond is an electron domain. So it has 1, 2, 3, 4. So that atom has 4 electron domains. So that means that one right there is actually sp3, right? 2, 3, 4, sp, sp2, sp3. Very simple. So if it has 4 electron domains, it's sp3. So that one is not an sp3. It's not sp, right? The question is how many of them are sp. So let's do the next one. The next one right here. Well, that one has a single bond, so that's 1. It has a single bond, so that's 2. And it has a double bond, so that's 3. Right? Remember, the double bond is 1 domain. A triple bond is 1 domain. So it has 3 domains. So that's sp2. So that one's not either. That one's not sp. So far, no sp. The last one here, it's got 1. There's a double bond. There's 2, and there's 3, right? So that's sp2, right? That one's also sp2. In fact, if you have 2 carbon atoms and they're double bonded to each other, and they just have hydrogens attached to them or carbons, they're going to be the same hybridization. So these are both sp2. So the answer for this one is none. None of them are sp. In order to be sp, you have to have 2 electron domains. Okay, here would be sp. Okay, let's take this carbon right here. It has 1 electron domain, 2 electron domains, so that's sp. This carbon right here, it has 1 electron domain, 2 electron domains. So that one's sp. Sorry, sp. Okay. So that would be sp. Okay. So organic chemists then are very quick at this. They look at it. Oh, yeah, I remember 2 domains, sp. 4 domains, sp2, sp3. 3 domains, sp2. because carbon, these are the only ones you have to worry about with carbon. Carbon is in the second row, so there is no sp3d. There is no sp3d2. Okay. Let me see, is there one more? Let me show you one more. We're just about out of time. Let's see. Okay, same thing with this one. This one has some oxygens in it, but don't worry about that. Okay, so for this one, they want sp2 carbon. So how many are sp2? Okay, so you only have to do the carbons. So we come over here. There's a bond, so that's one electron domain. Here's a bond, so that's another electron domain. Here's a double bond, so that's an electron domain. So 3. So then you come back, sp, 2 electron domains, sp2, 3 electron domains, sp3, 4 electron domains. So this one has 3, so it's sp2. Okay. A carbon that has 1 double bond and 2 singles is always sp2, sp2. Okay. We've only got one other carbon here. That's the one down at the bottom. Okay, so look at it. Count up the number of single bonds that it has, right? A single bond is 1 electron domain. 1, 2, 3, 4, sp3. Okay, so carbon like this is sp3. That's the conclusion. Carbon like this is sp2 if it has a double bond and 2 singles. Now, carbon can also be this, right? You can have 2 double bonds for carbon, so that's sp, and so is this. And notice I didn't show any where carbon has a lone pair. Again, that's an interesting aspect of carbon. It is relatively rare to find carbon with lone pairs. So in your periodic table, this is the most common form of fluorine, 3 lone pairs and a single bond. Oxygen, 2 lone pairs and 2 single bonds. Nitrogen, 1 lone pair, 3 single bonds. And then carbon, no lone pairs and 4 bonds. There's a cool pattern with that. Okay. So that's hybridization, which is valence bond theory. That's section 9.5. There's only 2 types of problems you got to do in there. The last topic in our course is 9.6, which is molecular orbital theory. Now, it turns out I have a meeting tomorrow that meets at the time that your class meets, that I've got to go to that meeting. So what I will do is tomorrow, I'm going to, before class starts, like probably around 7 or 7:30, I'm going to do a half-hour lecture, and I'm going to post it to YouTube. So it should be up by 9 o'clock, so you can just watch that half hour. And it's going to cover the first part of the last section, 9.5. And then on Thursday, I will finish up 9.5. So I'll do a little bit of it tomorrow. I'll post it to YouTube. And then on Thursday, I will finish it at our regular time at 9 o'clock. So then it'll be done. And then that's it. 9.6 is the end. So we're almost done with this. And it looks to me as though I still haven't graded the most recent exam, which was, I think, chapter 6, right? So chapter 6, I will start grading that this week. So look for your grades for chapter 6 to start changing. And the lab reports as well. I'll start working on the lab reports as well. Okay. So have a great day. And I hope you enjoy the bonding stuff, because it's actually very different from most of the stuff we've done in the course, and it leads very well into more advanced courses. So have a great day.